Hello, Calc students. Today we're starting section 2.2. This is actually section 2.2, day 1, limits to plus and minus infinity and beyond. First, let's look at a little definition of infinity. Infinity is not really a number. It is a destination. We can't solidify what infinity is because we can always add one to it. And with regards to negative infinity, we could always subtract one or subtract 0.1. So infinity is the largest number you can ever think of, and it keeps going up. So what we're going to look at is, as x goes to infinity, what is the y value of the function? All right, so here's our first function we're looking at, 1 over x. And by the way, we're going to determine the horizontal asymptotes with our x going to infinity. All right, we're also going to be looking at vertical asymptotes, which is when our infinity or the y value actually equals infinity. So we have horizontal where x goes to infinity, and the vertical where the limit goes to infinity, which is kind of like the y going to infinity. So let's look at the limit as x goes to infinity. These are very similar to end behavior models. And so you can kind of look at them like that. We'll talk more about end behavior models and day 3 of this section. So let's look at this algebraically and graphically. We have x going to infinity, first of all. And as x goes to positive infinity, this function gets extremely close to 0. And therefore, the limit is equal to 0. As the x value goes to negative infinity, it also goes towards 0. These graphs are getting infinitely close to the line y equals 0. This is where a horizontal asymptote comes in. I will show you the definition of that in a minute, but y equals 0 is a horizontal asymptote. And that's determined actually by both of these equations. That limit going to infinity and negative infinity. Both of them are showing that y equals 0 is a horizontal asymptote. You only need one of them to state that it's a horizontal asymptote. Okay, let's look at, oh, by the way, that's a graphical look at this. You can also determine this algebraically by taking, kind of like plugging in infinity for x. If you have 1 over a large number, it goes to 0. So that also reinforces the fact that algebraically and graphically we can see that 1 over negative infinity is also going towards 0. Okay, let's take a look at horizontal asymptotes, and these are the definitions of a horizontal asymptote. Limits going to plus or minus infinity. This limit, as x goes to positive infinity, if it equals a number, then y equals b is the horizontal asymptote. Lots of times, because I don't want to write all these letters, I will put HA. HA, horizontal asymptote. Y equals b. In this case, x is going to negative infinity, and therefore y equals b would also be a horizontal asymptote. HA, huh? Okay, that's a definition of a horizontal asymptote using calculus means. Okay, so graphically, we're going to look at this equation, and by graphically I mean take out your graphing calculator. We put in x over square root of x squared plus 3, we graph it. And I also changed the window on here of the y values from -3 to 3, just so that I could see the graph in more detail. So as x goes to positive infinity, this y value, remember limit is always a y value, is equal to 1. As x goes to negative infinity, gets smaller and smaller and smaller, the limit of this function is going to -1. All right, that tells me that this function has a horizontal asymptote at y equals 1, and it also has a horizontal asymptote at y equals negative 1. All right, those asymptotes horizontally are always the y values. Okay, next, we have a way to use the sandwich theorem for limits of x going to positive and negative infinity. Now, first of all, remember our equation from a couple lessons ago. And this is on your formula sheet. This is something you should memorize to help you out on the AP test and to help you out on problems in this section. This is very important. And the difference between these two sentences is where x is going to. X is going to 0. Remember, we used the sandwich theorem to prove that the limit was equal to 1. Let's use the same sandwich theorem, same principles, to check out what the value of this is. Okay, so we're going to start with sine of x, because we always know that sine goes from negative 1 to 1. All right, so next thing, we're going to divide everything by x. All right, and what we want to do in this case is make the middle part of this inequality look like the limit as x goes to infinity. So that's what we're going to do. Take the limit as x goes to infinity of all three of these parts. And that's legal to do. Oh, I actually wanted to go to infinity, don't I? X is going to infinity. All right. So as x goes to infinity, negative 1 over x. And this side is also 1 over x. That's a negative 1 over x. And then we have sine of x over x. Okay, using this sandwich theorem, the limit of negative 1 over x as x goes to infinity is equal to 0. The limit as x goes to infinity of 1 over x is also equal to 0. Therefore, the only place this could be is 0. So this limit up here is equal to 0. This is another equation you should memorize. You should memorize the limit as x goes to infinity, sine of x over x equals 0. Okay, now I can always help remember these by the fact that there's an infinity here and a 0 equal to. When there's an x going to 0, it's equal to 1. So you can never have a 0 and a 0 in the same place, or in the same rule. Okay, so we have properties of limits on page 71. I would advise you to look at these and to also do the, look at the example that goes with it. We will be doing some problems in our assignment. Sum, difference, product, constant multiple quotient, and product rule. Make sure you know all of those. All right, now we're going to use some fancy, we're going to use one of the properties and also fancy algebra to figure out this one. I'm going to distribute my 4x, which is on the bottom, to look like this. And this is an equivalent statement. I haven't changed the meaning of the statement. I just used my fancy algebra to figure it out. Okay, so now I'm going to simplify 4x divided by 4x is 1 minus sine of 4x over 4x. And we're going to take the limit as x goes to infinity of that. Now, by our properties, the property is the difference rule right here. It says the limit of one function minus another function is equal to the limit of one minus the limit of the other. So that's what I'm going to do, is separate this out and take two limits. Limit as x goes to infinity of 1 minus the limit of x goes to infinity of sine of x over 4x, or sine of 4x over 4x. Okay, and that's something we can do because of the difference rule. The limit of 1 is 1. The limit as x goes to infinity of sine of 4x over 4x is actually equal to 0, and therefore the total is 1. So these limits, sine of 9x over 9x are the same as sine of x over x. When you take the limit, x going to infinity, they're all going to equal 0 if you have the same number on the top and the bottom. Okay, and that is the end of our lesson, first part of. Thank you for tuning in. More limits tomorrow.